Okay, thank you. Thanks again for inviting me to this second workshop. A little bit less sick than last time, so hopefully I'll be able to give a proper talk. This is a joint work with Colin Sandon as a student at Princeton, and I'll talk about the recovering communities in the block model. The paper has been posted 2 weeks ago on arXiv. And I'll start by explaining what community detection is. So the problem is you're given a graph, a network, it's just a bunch of dots that are either connected or not. And you try to identify a partition of the graph into subgroups that are alike. So alike could mean that they are more densely connected, like in this figure. There are clearly 5 groups that are much more densely connected with only few connections across them. And communities are not necessarily denser groups. It could be that the relationship is disassociative. That means you connect more with people in the other community. That could be Facebook in the early years with males and females, genders. And so there's all sort of structures, but the common one is the one of associative connection, which is called clusters. So the animation is due to a student, Joao Pereira in Princeton, who spent a few nights on this, I think. So I'll play it again. This is if you were not to do the right clustering, if you just do an arbitrary partition of the nodes, you would get something which is like junk, see tons of connections and no structure. But there's only one here which is nice. It's the proper partition in the clusters.
Wow.
So,
Can you do it again?
I'll give you the movie.
The student's name is not even in the author list.
True, yeah, I should have put this. It's Joao Pereira. Let me write it down. All right.
I made the animation and all I got was a lousy thing.
Yeah, you got something. Yeah. I gave you some chocolate, Swiss chocolate. So applications of community detections, they're pretty broad. The field exploded with social networks. That's one of the first things you want to know about networks are community structures. Biological networks, protein-to-protein interactions. There was a talk just before about gene networks. Tumor classification, clustering was used extensively in these areas. Communication networks, Bell Labs is interested. This is a call graph, people talking to each other in a network communication. People are interested in 5G and understanding how to distribute information more efficiently by using the underlying social structure of the network. It's also applied to, these are problems where the network is, in a sense, natural. Then there's a whole bunch of applications where the network is engineered from data sets. For example, you have a collection of databases of images, and you connect 2 images if they share some common features. That gives you a graph of similarities, and then you try to detect clusters or community in the graph. Segmentation, recommendation system, advertisement, information retrieval. Broadly speaking, wherever you have some data sets of similarities and you try to understand groups of nodes that are alike, you rely on these methods. So the stochastic block model is a network model with so it's a random graph model with a cluster structure. And this is the model. I use this notation, SBM, with 3 parameters, N, P, and Q. N is the number of vertices in the graph. P is a probability vector. The dimension of the vector K is the number of communities that you have in your model. And Pi is the relative size of community I. Okay. So this is, for example, 4 communities of different sizes. This is there's roughly n times P1 nodes in community 1, n times P2 node in community 2, etc. Capital P I'm going to use for the diagonal matrix, where you put this vector P on the diagonal. And the third parameter here in the model is Q. It's a symmetric matrix with entries in 0, 1, and it tells you how a node in community I and J connect. That's the probability Qij that they connect. So here is all the possible connections. You connect with probability Q1, 1 inside, Q1, 2 in between 1 and 2, etc. So since the workshop is about information theory, I see this model as the DMC of clustering. DMC, for those of you who are not information theorists, is the discrete memoryless channel. It's a nice and reasonable model for community detection. Nice in the sense that, as we will see, there are very nice phase transition phenomena, like the capacity type of results. That gives you a good way to benchmark algorithm with a clear line of sight. It's reasonable in the sense that it's, of course, a model, so it's not exactly realistic, but it fits pretty well some cases of data. And also, just like the DMC is not a real model for communication, there's always memory and things like that. But out of this model, you can extend it with some variants with overlapping communities and things like that that actually become really practical. So it's a good model, I think. Now, just to see if we are okay with the parameters, this is the quiz. If a node is in community I, how many neighbors does it have in expectation in community J?
What are the options?
The options? You have to. Multiple choice. Okay. So I didn't have. It's true. Quiz for me doesn't have to be multiple choice, but I should have put multiple choice. So there's one choice I'll offer you. It's the answer. That's the number of nodes that there are in community J, and then you connect each of them with probability Qij. That's in expectation how many you have. So that's a matrix which is going to show up a few times. Remember, this is a diagonal matrix of the PIs times Q. That matrix, if you look at column I, it tells you the community profile, what a node sees like in its neighborhood, how many nodes in each community it has in expectation. All right, so the problem is when and how can we recover the clusters from the graph drawn from this model? When means for which P and Q you can solve the problem, and it's going to be with high probability when n tends to infinity. Of course, if Q, for example, is a matrix where all the entries are the same, then you have an Erdős-Rényi model because there's no trace of the communities. Everybody connects in the same way, so it's clearly impossible to find the clusters. But we would like to understand what measure of discrepancy of the Q entries is allowing you to tell when you can or not cluster, and it depends probably also on these P's. And how is also about efficiency of the algorithm, whether you can solve it efficiently or information interdictly only. So the next slides are about first the warm-up, the case of two symmetric communities, which is already pretty hard and got a lot of work on. Then new results about partial and exact recovery in the general SBM. And that's the model I defined just before. And I'll motivate and try to explain how I think this is really closely related to the channel coding theorem. And then since there's big data in the title of the workshop, I'll try to show you at least one case of how this fits on real data. So the model with two symmetric communities, also called the blended bisection model, it's very simple. You have two groups. The probability, the relative size are half, so two groups of roughly n over 2 nodes. And you connect with probability little p inside the groups for both groups and little q across. Now you ask, if you take a graph like that, you erase those colors, you shuffle it, I give it to you, can you recover the two groups? So there's a bit of history on this model. It was defined in '83, and there's been a lot of work. This is just a partial list, a mixture of computer scientists, mathematicians, and statisticians. That's recovery means that you really try to recover the cluster, so the node labels has to be correct asymptotically when n tends to infinity. All nodes labels must be correctly found, and the results look pretty much all like this. How close can P and Q be so that you can solve the problem? As we said before, P is equal, yeah?
We recovered almost all. So the probability is over what there?
Here, the probability is over the drawing of the random graph.
Okay, and you recover all of
All,
them.
this is all. Xn hat as to be equal to Xn, so all. That's exact recovery, yeah, the full thing. And it looks like this. How close can P and Q be so that you can solve this problem? If P is equal to Q, we know it's not possible, so you'd like it to be as small as possible. And the approach is basically algorithmic. People come with a new idea of an algorithm, they try it, and they see what they get. Then there's been a new line of work that started around 2010 for the past 5 years, where people have changed the figure of merit. Instead of recovery, they looked at detection. This means that you only ask for a reconstruction of the nodes that is positively correlated. The other extreme, instead of recovering the full partition, you just want something that has an Hamming distortion that is a little bit better than half asymptotically, where half is what you get with a random uniform guess. If you don't even look at the graph, you just flip a coin, you get 50% right. You want to beat that asymptotically. So this, what happened here is that this group of people, Dessel, Krauskala, Moore, and Zdeberova, they came up with a very precise and very nice picture for this model of detection in the symmetric case. based on statistical physics arguments, non-rigorous, but the result is like this, that they conjecture that if P and Q are scaling like a constant by n, with different constant, A and B, then you can detect if and only if you have this nice equation. So that's pretty amazing because it's an if and only if, and also they have an explicit formula. So it took a bit of work to actually prove that statement. This was done by Massoulier and Moselny-Mansley last year. And one way to interpret the result is this equation, you can rewrite it like this. That's another way to rewrite this equation. This thing here, that's a 1. This thing here is what you need to have a giant component in your network. And you know you need a giant for at least hoping for detection. And what this is somehow an oversampling you need to be able to detect. You need more than the giant. So at that time I was reading those papers, I thought this looks like an extension of the giant, but for recovery, we also know that we need the graph to be at least connected, which is more than a giant, which happens in the logarithmic degree regime. So why would there not be another phase transition for recovery? And in fact, this takes place. We could show it last year. If you take P and Q that scales with an additional log n factor, then you can recover the clusters if and only if you have this equation. And this becomes the oversampling that you need in order to recover as opposed to just having connectivity. So this improves the bound that were there before, but it also gives the sufficient and necessary condition. So it's that. Now there's another work by Moselny and Sly that obtained the same result pretty much shortly after this in an independent work where they have a more general result for A and B that can depend on n, as long as they are big theta of 1. So in both cases, we have algorithms that achieve the threshold. So on information theoretically, this is the limit, and you can achieve it all the way down to the limit. We have two algorithms in our paper. One is an SDP relaxation. So I'll just say a few words because it will connect to the next talk. The maximum likelihood estimator of the clusters from the graph is the mean bisection. You are trying to look for a partition of the nodes in two groups with the least amount of edges across the two groups. That's NP hard because you want the groups to have same size, to be balanced. So what you can do is you can write it with an SDP relaxation. And to ensure that the SDP gets you the ground truth, you end up with a probability on a random matrix, a random Laplacian of the stochastic block model. And you want to show that the spectral norm of that matrix is large enough so that you get that the SDP works. And if you do, in the paper originally here, we use a matrix Bernstein to show that the spectral norm is bounded in a certain way, and this is a little bit loose. It's roughly off by a factor 2. And there's been two works that allow to extend it. One is using the more powerful bound that Ramon will talk about in the next talk. And then also recently, He Yong with Bruce Hayek and Jieming Zhu obtained also removed the constant by using a Z. What's the name of the bound? Z?
Reduced to some result due to Zerina.
Zeriner, okay, sorry. Okay, so what's interesting is that it's not clear at all what happens for multiple communities. In fact, for detection, it's conjectured that starting when you have 5 communities or more, you no longer can achieve the threshold, which is information theoretic. We don't know what the threshold is, but with numerical experiments, people have conjectured that there's a gap between what you can do information theoretically and efficiently. And for recovery, there's no explicit conjecture that were made in our papers. So I'll address this question today. So how much time did I take so far?
10 more.
Okay.
10 more minutes.
So before I tell you the results, I'll tell you about why I think this is very closely related to coding theory, in particular the channel coding theorem. So in coding, what we want is we have n information bits that we want to transmit. There's a noisy channel. Of course, we cannot transmit them, the n of them, we cannot get them if we just pass them through directly the channel because this is noisy. But if we embed them into a longer code word, adding redundancy, then we can hope to recover the n bits from capital N transmitted bits. And Shannon told us that you can actually solve that problem with a ratio between the number of transmitted information and transmitted bits that is constant, the rate of the code. So if the noise is, let's say, a binary symmetric channel, that means you flip 0 to 1 with probability epsilon, and it's symmetric, then as long as the rate is less than this epsilon log 1 over epsilon, etc., then you can actually solve that problem. you can decode reliably those bits from there. So clustering this model is can be interpreted that way. You have n information bits. These are the community assignment of the n people in the graph. Yes?
What modification?
Oh yeah, sorry, thank you. Thanks. It's a bit embarrassing. I cannot write here, I think, but so you have again n information bits. That's your community assignment, n people. You look at each pair of nodes in your graph, and then depending on whether those nodes have the same label or not, you put an edge with different probabilities. So in the case of the block model, in the logarithmic regime, this will be your channel. If they are in the same group, so you look at, being in the same group or not is like looking at the XOR, so that's in fact a linear code. And then if they're in the same group, you put an edge with probability a log n by n, and in different group with b log n by n. Okay, that's your channel. So it's exactly a special structure code on a special channel. And the rate is fixed. That's the difference with channel coding. It's not a variable. It's 2 by n because there's n choose 2 possible edges. You can actually make the model different where you have measurements about the interactions of people with some rates, in which case the analogy becomes very precise with the channel coding theorem, but let's stick with a fixed rate for now. And then what we have is this property here, which is that again, you can do reliable communication. I don't know if you see it, but reliable communication is exactly clustering because decoding, so these guys here are the graph. Each variable is whether there is an edge or not between a pair of nodes. So that's the graph. And these are the community assignment. Decoding this from this is exactly reliable communication. So you can solve reliable communication if and only if you have this phase transition. So this equation here. That's 1 instead of rate because we are at the fixed rate. So now in Shannon's theorem, we have a much more general formula. It's not just for the binary symmetric channel. As long as you have, it doesn't have to be bits, it could be Curie bits with some distribution and an arbitrary channel here, you can succeed if the rate is below this maximal of the mutual information, where the mutual information is expressed in terms of the KL divergence. So the question I was wondering is there such a formula for community detection? If you don't have bits, but you have arbitrary number of communities, that means these are Curie bits. If you have an arbitrary channel, which is this Q that we had in the previous slides, is there again a general formula, and what would be the expression for J? So the result is as follows. If you're looking at the regime where you have logarithmic degree, that's where you need to operate to get for recovery, then you can in fact solve recovery if and only if this expression is more than 1. So that's your GPQ. And what is D plus? D plus is this notion of distance between two measures. It's the sum over of the convex sum here, so it's like an arithmetic mixture, minus the geometric mixture, and then you sum over all components and maximize over T. So that seems to be a pretty fun object. How does it relate to objects that we know? So I'll call this object without the maximization dt of mu and nu. So first of all, it's an F divergence. So that I thought was really cool because it's the same family of divergence and the KL divergence that we have for channel coding. So the clustering capacity is also using F divergence that Cesar defined in this paper in the 60s. I don't think it had an operational meaning up to this result. So it's actually not an F divergence if you maximize over T, but if you just plug half here, then it's the Ellinger divergence or distance. In fact, the maximization over T is at half for the symmetric block model, in which case you recover the result that we had before. This equation here is the same as, this is the rewriting this in the symmetric case, and this is exactly the same as a plus b by 2 more than 1 plus square root of ab. But if you are not in the symmetric case, then the maximizer may not be half, so it may not be the Ellinger distance. Then it's going to be something which is a generalization of the Chernoff divergence. So if you look at this object here, with the summation and with the max, you just put a log on top, then this is called the Chernoff divergence. But in our case, mu and nu are not necessarily probability distribution, so this sum is not necessarily 1, O after array. So in other words, this is a generalization of both the Ellinger divergence and the Chernoff divergence. So we call it in the paper the Chernoff-Ellinger divergence. That's what it's closest at. And the plus could be for either the fact that you maximize or for the fact that this is the Swiss flag for Communauté Helvétique. This was for QIJ non-zero. Let me skip this. So now, what can you do algorithmically? So we have an algorithm, which we call degree profiling, that achieves a threshold and not only is efficient, but it's actually quasi-linear time. So that means complexity is O to the n 1 plus epsilon for all epsilon positive. For epsilon as small as you want, as long as it's positive. So here I should say Colin did an amazing work getting this quasi-linear time. That's pretty hard. Quadratic is already a lot of effort. So showing that this was achievable efficiently is not easy, but making it quasi-linear was really a lot of dedicated work. So the conclusion is that for recovery, not for detection, you can actually solve the problem whenever it is information theoretically solvable. You can solve it efficiently. So there's no gap in that case between information theory and complexity. So quickly, 3 minutes. So quickly, sometimes you don't want to ask, can you recover exactly all the communities? But you could ask the question, which community can you recover? So here is how you solve the problem. You do an embedding of the communities. You represent them as the ith column of the matrix PQ. I call this a local community profile. This is a vector in R to the power k. And then you try to partition, to pack those points in a way that the CH divergence between any 2 points is more than 1. And this is the finest partition you can get. The largest number of groups you can obtain with this property is what you can recover. These guys, you must confuse them, but otherwise, these subgroups you can recover. Okay, so the proof idea, it's the message here is the following. Instead of sweating to get to the actual threshold in one shot with one algorithm, it turns out to be easier to first get 99% and then switch gear and use a different method to finish up the problem. It's more efficient. So for that, you need to know how to solve partial recovery, getting not everything but a constant fraction, and that's what I'm going to skip. And here is the algorithm how it works. You take your network, you split it into 2 networks. That's my last slide. And what?
Where's the real data?
Oh yeah, I'm skipping real data. I have to choose either the proof or the real. Okay, maybe we should. You want the real data instead? Okay, so I'll skip the proof.
No, I want the proof.
So I think I'm using my last minute with the debate. So I'll do both. So no. You split your network into 2 groups. On one group, you use partial recovery to get almost everything, and then you're left with an hypothesis testing problem. You look at a node and you say, is it more likely to be in this cluster or to be moved in the other clusters? And for that, you have to compare 2 Poisson distributions. Turns out that the error rate of that hypothesis testing problem makes the CH divergence come out. That was a very quick summary. That's how you have that thing that shows up. For the data, we took the blog networks. It's like about 1,500 blogs. All you know is which blogs puts a link to another blog. You have no other information, and you try to reconstruct which one is right or left leaning. And just out of curiosity, we plotted, we see what kind of parameters we would get if this was from a stochastic block model with 2 groups. We get those numbers, and this is just above what the threshold should be. This is the square root of 2. So in theory, if this were, you're not in the limit of n goes to infinity, but your n is 1,500, but in theory, if the model were to be fitting well here, you should be able to recover most of it, and we get 95%, which is pretty good with our algorithm. Thank you. Advertisement. There's a tutorial on information theory and machine learning at SIT if you're interested, and I'll stop here.
I have time for questions when Ramon sets up. So,
Yes.
So, one slide earlier, please. So, how do you get those numbers? Do you just count the number of edges to fit those numbers?
There's 2 ways. One is to use the fact that we know the ground truths, because people have checked the blogs, and you can take the ground truths to compute them.
Empirical average, right?
Yeah, that's empirical. This is all empirical averages.
Fit the model to the empirical average, right?
So I'm saying either in that case we knew the ground truth, so you can actually the 2 groups, so you can compute those parameters. But in general, you can also use the algorithm to cluster, and then use the clustering that you have from the algorithm, and then compute those parameters and see if they satisfy the equation. If they don't, then you have, in a sense, you have done some nonsense, because if the model was correct, you could not have recovered something meaningful.
so next speaker is Ramon.
Do you want this? No.
No. I have a